talks.
We haven't introduced you yet. What is this?
Sure.
Live stream. Got it. Good. Okay. So who's introducing Sam?
I can do it for you here.
No, not me. From today on, it's going to be how you's running.
Okay.
I just decided.
Yeah, I've been traveling a lot, so
That's all I do.
okay.
IT people.
Okay, so today we are very happy to have Sam here to from Berkeley to tell us about how to overcome the post-selection problem.
Hi, yeah, thanks all for coming and for the introduction. So yeah, I'm going to be talking about some work that's been in collaboration with Zach Weinstein in the first iteration, and then more recently with Edgar Altman in a paper we posted a few months ago. So yeah, what I'm going to be talking about is the barrier to observing the effects of lots of measurements, which is necessary for, say, observing the measurement-induced phase transition, and then one possible route to getting around that barrier. And yeah, as I mentioned before, please feel free to jump in with questions at any point.
Sam, I do have not a question, but suggestion. The majority of the audience here are students.
Sure.
So yeah, so make sure you speak to students, not to, measure zero faculties.
Got it. Yeah, no, yeah. So okay, hopefully the background for this should just be quantum mechanics. But please do stop me at any point if you want clarification or if I've said something unclear. Okay, great. So first off, a little some high-level background. So why are we asking questions about the effects that measurements have on many-body quantum states? So part of this is, of course, due to some amazing new technological developments in quantum simulation. So we now have some early, currently quite noisy, but ever less noisy quantum computers. And for some time, we've had a highly controllable many-body quantum systems in, say, optical lattices. So in these platforms, we now have fine control over the measurement process. That's really the thing I'm going to be focusing on today. And so, okay, why have we developed fine control over the measurement process? Why do we care about, say, measuring a single spin and not disturbing any of the others? Part of this is because of quantum error correction. So many schemes, almost all schemes for quantum error correction, I think all practical schemes for quantum error correction in dimensions lower than 4, require that you are able to perform measurements on sets of qubits, local measurements on sets of qubits which do not disturb their neighbors. And so this has now actually been implemented in a number of different places. So this is a figure taken from a paper by Continuum where they studied this for something called the color code. Google Quantum AI have been working on developing the surface code, which is it's also known as the toric code with open boundary conditions. So developing control of the measurement process is very important for this, and also from a purely scientific perspective. Its measurements have also been used recently to prepare topological states, which had not previously been encountered in nature. So these are some additional papers from Continuum where they were able to prepare both abelian and non-abelian topological order using local measurements of qubits, spin halves, and local unitary feedback. So the class of problems I'm going to be talking about today are kind of originally start with the measurement-induced phase transition. So I'll call them measurement-induced collective phenomena. So here in this setting, what I'm interested in is not using measurements to create something I'd sort of decided on in advance. What I'm talking about here is taking a many-body quantum system and asking how it responds to measurements. In particular, I'm going to be asking how these many-body systems respond to large numbers of measurements. So like one example of where this arises, as I mentioned, is the measurement-induced entanglement transition. So this was discovered 5 years ago by now, and so what the system that people were originally interested in here was say a spin chain. So think about a bunch of spin halves or qubits interacting with each other, and what we'll do is we'll let neighboring pairs of qubits evolve under unitary operators. So these gray boxes represent, say, 2-qubit unitary matrix that evolves them, and also single qubit measurements. So at some rate, you choose to measure your qubits, thereby disentangling them from their neighbors. Whereas the effect of the unitary dynamics is to entangle the different degrees of freedom. So there are 2 different limits you can think about here. So in one limit, there are no measurements. And in that case, your qubits become highly entangled and all local information is lost. And on the other hand, in the other limit, you just measure all of the qubits and you're left with a product state, which of course you can describe very easily. So in between these 2 limits, there turns out to be a sharp continuous phase transition, where you go from quantum states that have entanglement, subregion entanglement entropy scaling as their volume, which basically means that all the information on a local subregion is outside of the subregion. And there is then a transition to a areal or entangled state, which is to say that you basically, you're not too far from being in a product state. So another example of a measurement-induced collective phenomenon arises without dynamics, and this is something that we found a year or so ago by now. So if maybe random circuits aren't to your taste, you could instead just take an entangled quantum state, say the ground state of a critical system, and measure it. So let's say I gave you the critical ground state of the transverse field Ising model, and then I measured some large fraction of the degrees of freedom. Let's say I measure every other spin. Now, when I measure these spins, every time I do the experiment, I have some different random state afterwards, but that random state might look very different to the unmeasured state. So it actually turns out that for certain critical systems, when measured, they respond very dramatically to the measurements. That is to say that if you measure some finite fraction of the degrees of freedom, this can completely change the long distance correlations in the post-measurement state relative to the unmeasured state. On the other hand, there are also states which are in some sense robust to measurement. And as I just mentioned, another kind of measurement induced, I guess you could call it a collective phenomenon, or maybe you just call it a different approach to preparing a state, is what I just mentioned a moment ago, preparation of highly entangled states with measurements. I'm going to be focusing on these first two kinds of effects or phenomena, taking a quantum system which we understand in the unmeasured setting, and asking how this system responds to measurement. So there's a basic problem in this line of work, and that problem is that although we can theoretically study the effects of measurement on a quantum state, doing so in reality in an experiment is not so straightforward. So I'm talking about a setting where we take a many-body quantum system and we perform some extensive number of measurements. Maybe we measure 50 qubits. The problem is going to be that if maybe I should explain what this diagram is over here. So over here, as one example, we can imagine taking a bunch of qubits represented by these ingoing lines, evolving them in time, which is vertical, under some kind of dynamics represented by the gray box, and then measuring many of the qubits. So it could be that the post-measurement state, what I call rho m, so the post-measurement state here is the state that depends on the measurement outcomes, and is it's the state of the unmeasured degrees of freedom here. The problem is that this state is basically going to be different every time we do the experiment. So if we perform a large number of measurements, then the issue is, I should go through this in steps. So this is ready to set up notation because I'm going to use this throughout. So the problem is going to be basically that these states rho m we create are random every time. What we'll say is that capital M here is the number of measurements we perform. I'll label the outcomes by this string, which is lowercase m. So say, the outcome on this qubit, M0, this is M1, this is M2, and so on. And so for each particular outcome, we label our post-measurement density matrix rho m. And now the problem is going to be that, we've created this post-measurement density matrix. Maybe it's very interesting. Maybe it'll teach us something new about many-body quantum mechanics. But the problem is that we can't characterize it. So of course, to characterize a quantum state in an experiment, what you do, you measure it. So these m's, let's call them the preparation measurements, which gave me this rho m. But now I want to characterize rho m. And so to do this, I'm going to perform what I call a probe measurement. So to probe ρm, what I can do is I can measure, say, a Pauli operator. And when I do this, I find a result plus or minus 1, just one of the eigenvalues of the operator. And so what we'd like to do, of course, is we'd like to determine an expectation value. To characterize the state, we would like to determine some expectation value of an observable in that state, which here I'm denoting the expectation value conditional on M. The problem is that we can't even do this. So the issue is that in order to do that, we would need to repair ρm multiple times. Of course, to determine an expectation value in a quantum state, you have to repeat your experiment a number of times because the outcomes are random. The issue is that the probability that we ever see the same ρm again is exponentially small in capital M. It's exponentially small in the number of measurements we perform. So, as an example, let's say you had you measured 100 qubits and you wanted to characterize the state of one unmeasured qubit. The probability of each of those measurements might be something like 1/2. And so the probability that you ever get the same ρm again, well, it's 2 to the minus 100. So you're going to have to run your experiment 2 to the 100 times to see it again, which is, of course, impractical in experiment. So this is the regime we're dealing with. We're dealing with this. We're dealing with the regime where the number of measurements we perform to the number of preparation measurements we perform is so large that we're never going to see the same set of outcomes again. We're never going to see ρm again. Every time we do this experiment, we have a different set of outcomes. We know the outcomes. That's important. And we have a different ρm each time. And from each ρm, we can extract basically one bit of information by measuring it. Okay, is the kind of setup of the problem clear? I'm happy to take any questions at this point already.
Actually, I have a question. I think the sort of problem makes sense, but just out of curiosity, is the variance of the entanglement entropy with respect to measurement outcome, is that a very large quantity? And probably, I know the post-flux problem will still be a problem regardless, but it's more of just if you know the answer.
Yeah, no, so it's okay, it depends on the state. If I gave you a volume law entangled state, it would be quite small. I mean, most volume, like the variance of the entanglement entropy across states is quite small. The problem is that in a single run of the experiment, you can't determine the entanglement entropy.
Okay.
So it's if in a single run of the experiment we could just measure the entanglement entropy, the problem would be solved. The issue is that the entanglement entropy is nonlinear in the density matrix. So even though its variance happens to be small over states, we can't see it in a single run of the experiment. Yeah, thank you. Thanks for the question. That's an important point, and I'll return to that quite a bit later. Okay, so a fun kind of side comment on this this post-selection problem. Post-selection problem being the fact that in order to characterize our post-measurement state, we have to apparently post-select on a single set of outcomes. Now, okay, why is this post-selection problem interesting? I mean, okay, this is really a side comment, but it's something that I think is pretty strange. And that's this fact that if the quantum mechanics was modified slightly so that you could do post-selection, quantum computers would be much more powerful. They could solve everything. And so like this paper on the left here by Scott Aronson, 2005 or so. So what he shows in that paper is that in quantum mechanics, we know that the probability is the wave function mod squared, right? So what he showed in this paper is that actually if the probability was the wave function mod to the 4 or mod to the 6 and so on, if you change the Born rule, then you're actually able to simulate post-selection. He provides some trick for simulating post-selection, which is just getting the outcome that you want. And then the thing is, if you can post-select, then you can solve NP-complete problems with your quantum computer. So the fact that there is a post-selection problem and that we can't force measurement outcomes is actually a very serious constraint on the computational power of quantum mechanics. And so this is part of the motivation for understanding how far you can go in getting around it. Right. Okay. So now, okay, that was really a side comment. Back to the main part of the talk. So this is the question: how can we characterize these post-measurement states given that the outcomes are all random? Let's take an example, one that we might be a bit more familiar with. So let's say that we have two experimentalists, Alice and Bob, and Alice and Bob share a bell pair, up plus down for two spin halves. Now, what Alice can do now is Alice can measure her spin, and if Alice measures her spin, she'll find some outcome that's up or down. At this stage, when Alice and Bob are very far away, they haven't communicated. At this stage, Bob's description of his spin is unchanged. That is, so Bob's description of the state of his own spin is a maximally mixed density matrix. But now, okay, if Alice does send some information to Bob, if Alice tells Bob the outcome, the measurement outcome, then Bob knows the state of his qubit. And so what I want to illustrate here is that if you want to observe the effect of a measurement, you have to use the measurement outcome. Like if you perform a measurement in one location in space and you want to see the effect that it's had elsewhere, you have to find some way of using the measurement outcome. If you throw away the measurement outcome, that's basically what the environment is doing. That's like dephasing. So this is going to be a key part of our scheme. We're going to have to find some way to use measurement outcomes. So let's just outline this experiment. Okay, so we take some complicated quantum state, which is represented by this big box. In every experimental run, we measure and we observe some set of outcomes MR. In doing so, we create this post-measurement state rho MR. And then what we're going to do is we're going to characterize rho MR, our post-measurement density matrix, by measuring a Pauli operator. So we measure this Pauli operator, we get a result, and that result is plus or minus 1, right? So, okay, first guess is what to do. Let's maybe try and average the data. So no, that actually doesn't work. So the problem is that if you just average the data, then you're not using the measurement outcomes. And if you're not using the measurement outcomes, you might as well have let the environment measure those qubits and then not tell you the answer. So in that case, what you'd find if you just average over runs of the experiment, and this kind of comes back to this point about the entanglement entry before, if you just average over runs of an experiment, what you're probing is a property of the averaged density matrix rather than a nonlinear function of the density matrix averaged. So here, the point is that the average of the observed outcomes, plus or minus 1, is actually just the expectation value of the Pauli Z operator in the kind of average ensemble. So okay, there's another way we can think about this. So let's say let's write our observed eigenvalue. So zr lowercase zr. This is our observed eigenvalue. Let's write it in this kind of strange way. Let's write it as the expectation value, which is what we really wanted and which we were not able to access. Let's write it as the expectation value plus a fluctuation around the expectation value. Now, okay, what is this average doing? So the point is that when we just average these ZRs over the ensemble, we're washing out the noise, which is the second term. That's good. We wanted to wash out the noise. But we're also losing information on the variations of the expectation value of Z over the ensemble of M's. So what we'd like to do is basically still kill the noise, but hold on to the information on the ensemble of ZMR. So one kind of straightforward way you can do this is you can bring in some weights. I'm not going to tell you what these weights are yet. That has to be determined, and that's kind of the whole problem. So these weights, WM, I'm going to choose these to depend on the outcomes of what I call the preparation measurements, the M's, but they're not allowed to depend on ZR. They're not allowed to depend on the outcome of the probe measurement. And now the point is that if I take these weights, so every run of the experiment, now I have some weight that I determine somehow, I have freedom here. I have some weight and I have some outcome of my probe measurement. I multiply them together and I average. And when I average, I successfully wash out the fluctuations. And I'm going to hold on to the some information on the conditional expectation value of Z. Okay, so how should you choose WM? So as I've just been saying, that we can estimate these objects on the left. This is a strange but perfectly legal thing to do. The issue is, of course, that we have too much freedom here. These weights could be absolutely anything. Nevertheless, it did give us something. It gave us a way to kill the fluctuations, but hold on to the variations of the conditional expectation value ZMR over MR. So okay, now this is kind of what we started from back a year ago by now. So we started off asking, what's just the most aesthetically pleasing choice of these WMs? And okay, later in the talk, I'll get onto something that is not aesthetic, but I'll take a few slides. So one thing you might try, which gives you something that's not too awful, is you might try to choose these weights, WM, to be your theoretical estimates for the conditional expectation values. So C here indicates that this number is coming from some calculation on a classical computer. and C can stand for any calculation classical computer to your choosing here. But the point is that if you take this ZCMR and you multiply it by the observed outcome, so what you have is a cross correlation between your classical simulation on your computer and your quantum simulation through the measurement outcomes DR. So when we perform this average, we successfully wash out fluctuations. We're left with this cross correlation. And of course, we can compare this with theory. So we can just compare this with the theoretical estimate, which would be the square of the expectation value. And what I want to stress here is that because we're performing an average over something that depends on M, we're not just probing a property of the average density matrix anymore. We're probing the whole ensemble of post-measurement density matrices. And yeah, okay, so I should point out that this idea of using a classical simulation to observe some property of measurement, some property of some effects of measurement is not ours. I mean, this is just a different perspective on how to set this up. So the idea was introduced by Guns and Hughes back in 2019, where they introduced the idea of using the measurement outcomes as input to a kind of decoder, and that decoder would generate a local unitary transformation that in principle would allow you to observe the measurement-induced phase transition. A similar idea arose also in Yaodong Li and Matthew Fisher's paper in 2021. And what we've called quantum classical cross correlations appeared actually, or this kind of version of them appeared at essentially the same time in a paper from Zhongyon Li and collaborators. And also just to point out that this isn't all just a fantasy. It was actually this kind of scheme was implemented in a real live quantum simulation by Jesse Hoke, Matteo Politi, and the Google team earlier this year. Okay, so this is where we were about a year ago. There are some problems which I'll get to in a moment. So let me just sketch the kind of setup now. So we say we take our quantum simulator. Oh, sorry, is there a question? Okay, sorry, no, I heard some noise from somewhere. So we take our quantum simulator, we perform a bunch of measurements to create some post-measurement state, and then we're going to try and probe it. We probe it, we get this ZR. And now we can do something else. We can also throw these measurement outcomes, MR, into a classical computer, here represented by an abacus. The abacus, by playing with this abacus for some time, you generate this classical expectation value. And now what you can do is you can take the result of the quantum simulation and the result of the classical simulation, multiply them together and average to get your quantum classical cross correlation, and compare this with the classical cross correlation. So this is just diagrammatically a diagram showing what I was just talking about in the previous slide. Another thing I really want to stress here is that this scheme only requires classical post-processing. So you can implement all of this if somebody maybe already has some data from a quantum simulator, they've measured a bunch of qubits and they've kept track of the measurement outcomes, then that kind of list of bit strings is enough to look at to construct objects of this form. But right, okay, so I mentioned a moment ago I get onto the problems. The first problem is that the way we constructed these things is sort of completely arbitrary and driven by aesthetics. So we could have multiplied by the expectation value of ZC. We could have multiplied by this thing here. We could have multiplied by its square. We could have multiplied by its sine. There are many different options there. The second problem is that because of this, okay, they're really the same problem. Our experimental measurement results, which is our cross correlation between experiment and theory, which is supposed to kind of replace the standard experimental result. This result is now sensitive to our theory. So we've created this kind of barrier between us and what's really going on in the quantum simulation by changing the rules of the game like this. So what this talk is really about is a way of learning something about simulation independent quantities. How can I learn something about the quantum state itself and the effects of measurement on the quantum state itself without post-selection? Okay, and that's what I'll get onto through the rest of the talk. So are there any other questions so far?
I had a question. Is this restricted to a certain class of problems, or is it general to any kind of system?
It's general. What I'm going to talk about is completely general to any kind of measurement problem. So it can apply to, you can apply to random circuits, you can apply it to the effects of measurements on any quantum state of your choosing. So it's a general way around post-selection problems in many-body quantum systems. And actually there, you could also probably also apply this in a classical setting. So like, as an example of what that might mean, you could say, well, I have some classical system and I don't know its state. There's some complicated probability distribution describing all the possible states my classical system can have. And I might want to understand the effect that extracting some information on that system has on the probability distribution of the unmeasured degrees of freedom. So you could also apply it in that setting. Although in the quantum setting, there's an extra there's an extra interesting thing that arises basically as a consequence of the okay, maybe that I'll get onto in a bit. But yeah, so the approach is general and it also applies in the classical setting, is what I should say for now. Okay, so okay, right. So this question of can we learn something about simulation independent quantities? This was okay, this was kind of what we were addressing in this paper from back in the end of May. And I should also flag some very interesting recent work which has kind of arrived at many of these results from a different angle. And this is a paper for, oh, sorry. Okay, I should have removed that. It wasn't yesterday, it was now a week ago. This is a paper from Max McGinley in Cambridge, where he's given a kind of broader overarching perspective on what I'm about to tell you about. Okay, what I'm going to talk about is basically how to learn something about the entanglement of the post-measurement state without post-selection. So in order to do this, I'm going to have to describe a kind of slight variation on what's now a popular theme. I'm going to show how to apply the ideas from classical shadow tomography now in the context of the post-selection problem. So in our setting, we have some post-measurement density matrix, and it's different every run. So what we're going to do now is we're going to apply a random unitary from some to design, and we're going to measure in the computational basis. You could also think of this as just measuring at a random basis. But what I want to stress is that everything I'm going to say now, I'll focus on a single qubit, but it also applies to arbitrary numbers of qubits. It's just that it's probably simplest to describe in this way in the first instance. So, okay, we have our post-measurement density matrix. We don't know what it is. We applied a random unitary and we performed a measurement. I'm not sure why the outside vertical parts of my browsing cat are missing, but yeah, I think you can see what this means. So this ZR is the computational basis state corresponding to outcomes DR. It's one of the eigenstates of the Pauli Z operator, and it's the one that I observe in run R. A UR is a unitary that I chose. So what I do is I define this. What Robert Huang and collaborators do is they define this strange object, which they call a classical shadow. And this classical shadow, it has a kind of very simple property. So let's imagine, just like step back from the post-selection problem for a moment. Imagine that we could prepare rho MR many times over. Maybe the number of measurements we perform is quite small. But imagine we had access to the same rho MR many times. And what we could do is, take all these different rho MRs that we have lying around, apply unitaries to them, and then measure them. And then in this way, construct a large number of shadows corresponding to the same rho MR. Now, a shadow is defined, okay, the actual definition, well, the actual expression in terms of U and Z isn't all that important. The important thing is that a shadow has the property that when you average it over U and R and Z, you get the density matrix. So in a similar way, in kind of an analogous way to saying that you get the expectation value of an observable by averaging the eigenvalues you observe, the shadow generalizes this idea to matrices. So the shadow is the object, the shadow is to the eigenvalue, while the density matrix is to the expectation value. Averaging the shadow gives you the density matrix. So another way of saying that is that a useful decomposition of the shadow is that we can write the, sorry, was there a question or? No, okay. So we can take the shadow, which we observe rho SR. We can always write this shadow as, well, okay, this is a trivial rewriting, so of course we can write it in this way, but a useful way to rewrite this is as the actual post-measurement density matrix that we care about, plus a fluctuation around the post-measurement density matrix. So now when we have a post-selection problem, let's go back to this setting we're interested in. When we have a post-selection problem, we get a different rho MR every time we do the experiment. We get to see one shadow. We get a single shadow from the density matrix. So we can't extract that density matrix itself. But what we can extract is that density matrix plus a fluctuation. And this is, as I was saying before, it's the kind of matrix analog of the expression I wrote down before, which was eigenvalue is expectation value plus fluctuation. So let's now just kind of repeat what we did earlier. So let's take our shadow and multiply it not by a scalar weight, let's multiply it by a matrix valued weight. So WMR is now some matrix that I choose and which depends on the measurement outcomes. If I multiply the shadow by this WMR and I just average over runs of the experiment, I wash out fluctuations and I am able to access some property of the ensemble of post-measurement density matrices. So again, we have this problem. We have this kind of aesthetic. We have this freedom to choose something useful or maybe just something that's aesthetic. So here I'm going to show a useful choice of WMR. So what we're going to do is we're going to choose this matrix WM. We're going to choose it to be minus log of the classical estimate for the density matrix. Now this might look a bit weird, but you'll see why in a moment. So the idea is we have some measurement outcomes. Given those measurement outcomes, we maybe have some way of predicting what the density matrix should have been. And maybe it's an approximation, but we have some guess for what the post-measurement density matrix should have been. WM is minus the log of this object. The point now is that we can average, if we average this thing, average the left-hand side over experiment. So every run of the experiment, we get some shadow, we get some rho C MR, our classical guess. We can construct the log of that, take the product, trace, average. We wash out fluctuations and we get this thing on the right. So what I'll define the right-hand side as, let's call it the quantum classical von Neumann entanglement. So the actual von Neumann entanglement entropy would be defined as this object, but without the C here. So the quantum classical entanglement is the real density matrix multiplied by log of the classical estimate of the density matrix, so all with the minus sign. Okay, so now this is just some other quantum classical cross correlation I can construct, but why is this one particularly interesting? Well, it's particularly interesting because it's actually a contribution to the quantum relative entropy or quantum KL divergence. So again, there's a vertical line missing here. I'm not sure why there's a missing. But the quantum relative entropy, which is defined here, is always greater than or equal to 0, just from the way it's constructed. And what this means is that we can you can just kind of move one of these terms over to the other side of the inequality and see that this object, SQCM, averaged, which we do have access to in experiment, is actually an upper bound on the true averaged entanglement entropy. So, okay, this is the important result. This bound shows you that you can actually use cross correlations between simulation and quantum and classical simulations to bound properties of just the quantum simulation. So in other words, you can really probe physical quantities without post-selection using this cross correlation. And so I mentioned before I was thinking about a single qubit for simplicity. This bound is completely general. If you constructed shadows for a larger region and then use those to construct this SQC object, the bound would also apply.
Excuse me.
Okay. Sorry. What's the?
Do you have a sense of like when the equal sign will be saturated? Like, what's a physical picture of that?
Yeah, okay. Thanks for the question. Yeah, so I should have mentioned this. So the equal sign is saturated in the case where your simulation is perfect. So if you have an approximate simulation, you'll always find that the average of SQC is greater than the true entanglement entropy. And so this means that even if you don't know very much about your quantum system, any number you get on the right-hand side here, it's still telling you something that's potentially useful. But it's only as the simulation becomes perfect that then you're able to, that then you can really determine the entanglement entropy.
What is a perfect simulation test?
Okay. So let's say, as an example, to be really concrete, I have some quantum state that I've prepared on my quantum simulator. and I can store I can also store this state on my classical computer. So when I go to my quantum simulation and I measure this state, I get some outcomes. I can then, the point is that I could then simulate the whole experiment on my classical computer. So I get some outcomes. I then go over to my classical computer. These measurement outcomes define some projection operators that I should apply to the classical representation of my state. So I'm able to, simulate the effects of the measurement on my classical representation of the state, and then determine the classical estimate for the post-measurement density matrix. So that is the perfect simulation really means rho Cm equals rho m.
Thank you.
I have a follow-up question on that. So when you say perfect, that means rho Cm is equal to rho m, but if your quantum computer is not perfect, that means you need to have a perfect noise model and be able to run a classical simulation of that. Is that true?
Yes, yeah. So yeah, exactly. So if the system is noisy, you need to simulate the noise, but the bound still holds. Right, yeah, okay. Thank you for the questions. Yeah, I should have mentioned both of those points. So right, okay. So now let's go on to an application of this. So far, I've been talking about, general points about the measurement-induced entanglement, but it's probably useful to see some examples. So let's think about the measurement-induced entanglement transition. So as I was saying before, in this setting, we can imagine we have some spin chain. We evolve the neighboring spins or qubits under two-site unitary gates, and then we perform projective local measurements at some rate. So for P here is the rate of the measurements. For small values of P, the state is highly entangled. For large values of P, the state is weakly entangled. The reason that this transition is particularly interesting in this setting is that if the state is highly entangled, we can't simulate it. Like the classical memory that would be required to represent this state would be exponentially large in the number of qubits. Whereas for P greater than PC, we have efficient ways of simulating these states using tensor networks. So the setting the kind of probe will consider, as I was hinting before, is where after evolving this is the state after evolving the system for some time under unitaries and measurements, let's imagine measuring all but 2 of the final qubits. So these are our preparation measurements. Well, all of these are our preparation measurements. So after evolving our quantum state and measuring the bulk, we're left with some pure state on the 2 ends of the system. And we want to determine how entangled these 2 qubits are. So if we ask, what does the measurement-induced entanglement transition mean for this particular probe? It's that, for low measurement rates, the state's highly entangled, and what this ends up meaning is that even after measuring these bulk qubits, these 2 end qubits remain highly entangled. Their entanglement entropy in particular doesn't depend on their separation. In the area law phase at large measurement rates, then you find the post-measurement entanglement decays actually exponentially with the system length. And then at the critical point of P equals PC, you should find that the post-measurement entanglement decays as a power of the system size. So this is the kind of thing we'd like to observe. So okay, I didn't actually do this on a quantum computer, I admit it. My quantum simulation will here be, what I want to emphasize here though, is that the quantum simulation in an ideal world has, of course it has no noise in the ideal world, but the point is that a quantum simulation doesn't have a memory limit like a classical simulation does. So what I want to emphasize is the effect that the difference between a quantum and a classical memory has. I want to emphasize the difference in between these 2 kinds of memory on observations of the measurement-induced phase transition. So the quantum simulation will be exact numerics. We evolve the quantum state up to a time that's of order the system size. We measure all of the bulk qubits, and then we're going to extract a shadow of a boundary qubit. The classical simulation, on the other hand, I'm going to demand uses only polynomial classical memory. So here I'm going to kind of to emphasize this point. On the classical side, I'm going to be sorry, I should be saying they're both the classical sides. On the classical, in my classical simulation, I'm going to use tensor networks with a finite bond dimension chi, and this bond dimension chi is only going to be allowed to be at most a polynomial of the system length. So the memory required to store a tensor network with a bond dimension chi is of order L times chi squared to store all of the different tensors in your matrix product state. And at P equals PC, you might expect that since it turns out where you have logarithmic entanglement, this should give you a bond dimension that's polynomial in L. So now from our quantum simulation, we got some shadow and we also get some outcomes, which I'll call MR, and we'll throw these outcomes into our classical simulation, which will then spit out our classical estimate for the density matrix rho CR. And then what we'll do is we'll combine these two things into our shadow classical entanglement entropy. So rho minus rho s times log rho C. Okay, so what do we see? So let's first off think about sweeping across criticality. So let's fix the system size and vary the measurement rate. So first off, let's look at the exact results. The exact results are represented by these white dots. This is the entanglement between the two boundary qubits after measuring all of the bulk degrees of freedom. So we have now the next thing to look at is the upper bound. So the upper bound, average of SQC, this, how good an upper bound this is controlled by the bond dimension in this setting. So the limit of a perfect simulation here corresponds to the bond dimension being unbounded. It corresponds in this case to the bond dimension being 2 to the power of L over 2. And so 2 to the power of L over 2 in this setting is, what is that? So we have 20 qubits, so it's 2 to the 10. So the perfect simulation in this case would correspond to chi being 1024. So we're well below a perfect simulation. Nevertheless, you see that the upper bound represented by the solid lines here. The upper bound is decreasing as we improve the quality of the simulation. So you can see that over in the area law phase where the measurement rate is very high, even a bond dimension of 16 is pretty good. That gives you an upper bound that's not too far off the exact result. Of course, in reality, you would never know the exact result, but this is the benefits of just running everything on your laptop first off. But then as you approach the critical point, you see that you need an ever larger bond dimension in order to get a good upper bound. So at the critical point itself, you can see that even with chi equals 64, you're not quite there. But then for P less than PC in the volume law phase, which P is around 0.16 to be clear, once you're in the volume law phase, it's just a complete disaster. In the volume law phase, we know we need exponential classical memory. So we need our bond dimension to scale exponentially with the size of the size of the subregion. Chi equals 64 is just not enough. And so if you go to even P equals 0.12, you can see that the bound is a complete disaster. It's way above the true data. The other way we can get some insight into what's going on here is just by thinking about what's going on in the classical simulation. So we have our quantum classical simulation, but we can also just compare with theory. And so the theory here corresponds to just calculating the entanglement entropy in the MPS simulation rather than cross-correlating the MPS and simulation exact numerics as over here. So if we do just the MPS simulation, then of course, what the tensor network is doing is it's discarding entanglement. It's saving classical memory by discarding entanglement. And so we should generally expect the classical entanglement entropy or the theoretical estimate to always be below the true data. And this is also what we see. So the SQC is rigorously greater than the white dots. This other bound is not rigorously smaller than the white dots, but it nevertheless gives us some insight into what's going on. I'll talk about a better lower bound actually after I talk about the measurement-induced phase transition. Okay, so here we see that you can think of the measurement-induced phase transition as the point when your simulations break down, and therefore also the point when you can no longer see what's going on. But let's also think about what's going on. Sorry, is there a question?
Yeah, quick question. So from the SQC guy, you can kind of get a sense where the phase transition is, even if I'm not told what the value of PC is. But from the SCC guy, if I just look at the SCC, it's very hard to tell where PC is. Am I understanding correctly, or you have some way to even estimate where PC is just using SCC?
So we're not, good question. So SCC for this particular probe happens to not be extremely sensitive to where the transition is. So but I suppose our aim here isn't necessarily to detect where the transition is, and this is partially because well, somebody had happened to have done it already, so there was some. Actually, I somehow left out the reference here. I'm using I'm not trying to detect where the transition is. Using SCC, if you wanted to detect where the transition is using a purely classical simulation, there are better ways to do this. And so actually P equals 0.6 was estimated by Aidan Zabalo and collaborators in a work a few years ago. But yeah, so the point is that if you wanted to detect the transition with a purely classical probe, there are better ways to do it than using SCC.
Okay.
But yeah, okay, you're right. That SQC is obviously an extremely sensitive probe because the bound just blows up as soon as you get to the transition. Right. So next, next let's ask what's going on actually at criticality. So at criticality, we expect the entanglement entropy to decay as some inverse power of the system size L. And so, okay, and this dotted line here is just a fit to the white dot, the exact results, which I've offset from the data. And so again, we can see a similar kind of behavior. So we see that the classical simulation, as you go to larger and larger system sizes of fixed bond dimension, your simulation gets worse, this bound gets wider. And if you look at SQC, if you look at the quantum classical entanglement entropy, this is again a complete disaster. As soon as you can see that for any fixed bond dimension, as there's some particular L you get to where the simulation just flies off to give you some absolutely useless upper bound. So the question then, based on the right-hand side, is how large a chi do we need to see criticality at a given L? And this is going to basically underlie the this is really the basis of one of the main results of this work. So I mentioned before that so at criticality, in general, even away from criticality, the memory required to store your matrix product state goes to the system size times chi squared. Now, sorry, I'll go back a bit there. So at criticality, there's also supposed to be no length scale in the problem if chi is infinity. But so now what we can imagine, we could imagine that when we introduce some finite value of the bond dimension chi, this introduces a length scale, introduces some correlation length, because representing power law correlations requires infinite bond dimension. So what I'm talking about here is really, so it's really an insight that came through the theory of finite entanglement scaling, formulated now, 15 years ago. So the theory of finite entanglement scaling wasn't anything to do with measurement induced criticality. It was just to do with conventional quantum criticality in one-dimensional systems. So what this theory described is the classical memory that was required to study ordinary quantum criticality on a classical computer. So basically what it describes is how much memory you need to represent a critical state in a finite size system. And so this theory tells you that if you have some finite bond dimension, this should introduce some length scale that is a power of that bond dimension. So here, what we're going to do is something slightly different. So what I want to understand is I want to apply this kind of idea, but now to the SQC, now to the cross correlation. So what I want is to quantify the classical memory that was required to observe measurement-induced criticality on a quantum computer. And so, so what we can do is we can take this plot I showed you before. I'm just showing you on the right-hand side of the previous figure, I showed you all these lines that were kind of flying off to infinity as I increase L. What I can now do is I can ask, well, if there is a characteristic length scale that's been introduced by my finite bond dimension, I should be able to collapse my quantum classical entanglement entropy using this form here. So what I can do is I can take a number of different system sizes and a number of different bond dimensions, and I can plot the appropriately scaled quantum classical entanglement entropy. And I indeed find this kind of remarkable collapse over a kind of a large range in bond dimension. And so what this is showing you is actually the way that your simulation breaks down at the critical point is actually the observable signature of criticality. So you could, and what I want to stress is this figure on the lower right here is something that's in principle experimentally accessible. I'm just looking at the quantum classical object. So this is the I'm seeing that the way my simulation breaks down is it seems to follow this kind of universal form. And additionally, I know that this line here is always greater than the appropriately scaled true entanglement entropy. Okay, so now, okay, I have not so much time left. I'll sketch an additional bound we can get on the post-measurement entanglement. So, okay, so far what I've talked about is just a bound, but it would of course be really nice to actually know the entanglement entropy. And so I'm now going to show you how you can do that in certain settings by finding also a lower bound on entanglement. So now let's fix notation. So let's say our post-measurement state lives in a bipartite system, A and B. Rho M A B is the actual post-measurement density matrix for those regions, and this rho C M A B is our classical estimate. So the relative entropy of the KL divergence is given by is defined in this way, and actually it's the relative entropy has this very useful property of monotonicity, which tells you that actually the relative entropy of a subregion of AB is always greater than that for A. Now, this looks kind of abstract, but it has a really kind of intuitive meaning. So the relative entropy quantifies the difference between two distributions. So what I'm saying here is that the distance between a distributions defined on AB is greater than or equal to the distance defined over just A, which is like saying that if we have some distribution over distribution describing the state of many degrees of freedom, if we throw away some information on some of those degrees of freedom, the two distributions can only get closer together. So that's like basically just saying throwing away information decreases the distance between probability distributions. Now, the important point is that because the entanglement entropy is always greater than or equal to 0, this object on the left is always less than the entanglement entropy of region A. So what that means is that whereas just this first term, SQC A conditioned on M, was always greater than or equal to the right-hand side, the difference between SQC AM and the entanglement, the quantum classical entanglement entropy of AB, this is always less than SAM. So what this tells you, this is just combining the two bounds. What these two bounds are telling you are that if you care about the entanglement entropy of a subregion A, and you're able to identify a region B such that AB is almost pure, such that this SQC ABR can be made very small, then you can determine at the post-measurement entanglement entropy without post-selection. And then some other bounds I can sketch. So turns out you can also, this is now just like kind of the end of the talk, but I just had some other bounds to throw in here. So you can also bound the purity using, okay, it's much simpler. If I take the real density matrix and then the classical estimate of the density matrix, square it and trace, I find this bound on the right here. Similarly, you can get a lower bound on the entanglement negativity. So the negativity can be expressed in this way on the left-hand side. So rho TAM is the post-measurement density matrix for say AB, partially transposed in A. And once you take this partial transpose, the density matrix is not necessarily completely positive, but it's still a Hermitian. And so basically negative eigenvalues of this density matrix, of the partially transposed density matrix, tell you that your state is entangled. So if your state was entangled, you end up getting some negative eigenvalues. You can then define the projector onto the space spanned by the corresponding eigenvectors. And then the negativity is this object. But now you can see that actually if this is the true negativity, which you can't determine because you don't really know rho TA, you can nevertheless lower bound it using a classical estimate for what that projection operator should be and multiplying it by the partial transpose of your shadow and then averaging. Now, actually, credit goes to Matteo Politi for this one, who told us about it after we posted the first version of our paper. Okay, thanks for listening. This brings me to the end. Okay, I talked about how if you want to observe the effects of large numbers of measurements, you have to run your experiment in a slightly different way. So the things you have access to are cross correlations between experimental data and your classical simulations. the key result of our recent work was to show that you can actually construct cross correlations in a specific way so that they bound simulation independent physical quantities. In this setting, then you see that basically the ability to observe a phenomenon is tied closely to your ability to simulate it. And of course, you know, the kind of larger outlook here is that there are new kinds of experiments you can do in noisy quantum simulators by, say, determining unambiguously the effects that measurements have in a quantum state. And this is now becoming, you know, a reality in a wide variety of platforms. So, right, thank you for listening.
All right.
Yeah.
Manage questions?
Any other questions?
Yes, I have a question. So you said this classical quantum cross correlation, it overcomes the post-selection problem, right? But to calculate the classical shadow, you still need to post-select the measurement outcome. So how does it overcome this problem?
So to determine it, okay, I'm only extracting one shadow. So in order to use classical shadows to reconstruct a density matrix, I would have to repeat the experiment and post-select. But I'm not doing that. It's that every time I run the experiment, I get a single row M. I only ever see that row M once. I extract one shadow from that row M. So I'm not determining, and so that allows me to construct this one matrix that is not a density matrix, and then I can average that with some matrix valued weight. But I'm not having to. I'm not using classical shadows as it was originally designed as a way to reconstruct a density matrix through an average. I'm just using the insight that there's this object that you have whose average is the density matrix, even though I can't explicitly do that average.
So just to make sure, like you said, the post-selection problem becomes a variational problem. So that's basically you're saying you're running the experiment still multiple times, but every time you get a different outcome. Wait, but I don't understand what's that statement. So you said it becomes a variational problem, but
yeah, right. So
the variation.
So let's imagine that I've created I take some quantum state and I prepare that initial quantum state many times on my quantum simulator. Every time I measure lots of the degrees of freedom, and I want to characterize the effects of those measurements on one qubit at the end. So now every time I run the experiment, what I'll do is I'll extract a single shadow. And so my data now consists of a string of measurement outcomes from the middle of the system and a single shadow extracted from the final qubit. And now, okay, the experiment's done. I store this in my classical computer. And now I ask somebody, can you tell me the effect that the measurements have had on the entanglement? So then somebody comes along with a model for your quantum system. But the model has some variational parameters. You don't know exactly what the model should be, but you have some kind of ensemble of possible models that could describe the system where, say, maybe you don't know the gates exactly. Maybe you want to vary the different gates in your circuit that prepare the state. So the point is that for any given set of model parameters, I could calculate the measurement averaged quantum classical entanglement entropy. And I know that that's an upper bound on the true measurement averaged entanglement entropy. But this bound is only saturated in the limit of a perfect classical simulation. So why don't I just take the average quantum classical entanglement entropy and see how that varies as I change model parameters. And so what I want to do is basically choose the best model parameters such that my SQC average is minimized. And then that tells me that I have a good model for my system.
Oh, so parameters are only for the classical simulation.
Yes, yes.
Okay, makes sense. Thank you.
Sorry, yeah, no, okay, very good point. Yeah, I'm not talking about any kind of like quantum variational approach. It's completely classical variation, but it's using input from a quantum simulator.
So Sam, I was admittedly distracted by March meeting abstract deadline, but very good, I know. But the classical simulation, needing this classical simulation, does that limit your circuit to what is simulatable?
Yeah, very good. Yeah, very good point. Yes, it seems so. Like the
and that's sort of the state of art for everybody, right?
Yeah, this is the kind of mysterious thing about the post-selection problem. It's that it seems that you can't observe a measurement-induced phenomenon that you couldn't actually just simulate on your classical computer.
The funding agencies better not know this.
What was that, sorry?
Joking, never mind. So that seems to be a big limit, right? If we are always only limited to study what can be classically simulated, doesn't that seem to be a limit?
Yeah, of course. No, it's a huge limit. I'm not going to pretend that that's not a limitation, but it's been very interesting to figure out exactly how that manifests here. But
Yeah.
I think the outlook here is slightly different, though. It's that there are situations. Okay, let's suppose that we have some very complicated quantum state that we definitely can't store on a classical computer. But then we measure, and we can't store it in a classical computer because it consists of, say, 100 is, a state of 100 qubits. The memory is 2 to the 1. Memory required is 2 to the 100. So of course I can't represent this thing on my classical computer. But okay, then I measure 98 of the qubits, and I'm left with a 2-qubit state. Now there's no reason I couldn't. I mean, this is a 2-qubit state. I need 4 numbers to describe this thing. There's no reason I shouldn't be able to do that. So, but this is, in principle, a setting where you could apply this kind of scheme. And this basically raises the question of whether there are settings where you can't describe the unmeasured state, but you can describe the post-measurement state. So in that setting, this scheme would become useful.
Any other questions?
I had a question. When you showed the critical collapse of the, I guess that was SQC.
Let's go back to that. Yes, right.
Yeah. What happens if you do the critical collapse for the, I guess, SCC, the classical thing? Is it also as max or?
Yeah. Okay. Good question. So the critical. Okay. So we haven't put this in the paper, but I mean, basically because the system sizes I went to were not large enough that it looked interesting. Like if I go back into the previous slide, you can see that the way that the classical simulation fails is not particularly spectacular. But there should in principle be some other length scale. If I bring in a finite bond dimension, there should be some length scale introduced at the critical point that just manifests in the classical simulation. And so this would really be the length scale that's more analogous to the subject of the theory of finite entanglement scaling. So, but yeah, okay, I can say I can create a set of curves that look like they collapse, but the curves almost collapsed even before I scaled anything. So I can't conclude that I have a critical collapse. For now, I don't believe there is my expectation is there should be a nice critical collapse that you can get at larger system sizes. And developing a theory for how the chi-induced correlation length depends on chi is a very interesting question, which is an ongoing area of work. But actually, I should say, in principle, there's nothing stopping you from going to larger system sizes than I went to here. The point is that because my focus was on the cross correlation, I was focusing on system sizes where I could also do a classical simulation. An exact simulation, which is to say I stuck to system sizes up to about 24. But if you were just interested in the effect that a finite chi had in your tensor network simulation, there'd be nothing stopping you from going to hundreds of sites.
Another question? No, that's thanks, Sam. Okay.
Right, thanks all for coming.
Thank you. Thank you very much.
Thanks so much, Sam. Have a great weekend.
Thanks, you too. Bye. Thanks for organizing this.